Okay, so I will start with one more example of an NP-complete problem and then move on to dealing with NP-completeness, right? So this is simple enough, so I thought I should try it out. So you are given a 2CNF formula. So remember, CNF means conjunctive normal form. Which means basically ands of R's. Okay, so each clause is a R of some literals and then you want and of the whole thing. And 2 refers to every clause is at most 2 variables. And I told you, I think it is in the assignment, that testing whether there is a satisfying assignment is polynomial time solvable if the number of variables is at most 2. But now I am asking, you are also given an integer k. The question is, does there exist a satisfying assignment with at most k ones? Okay, is the question clear? That you want an assignment. So typically maybe ones are costly, so I want to minimize the number of ones I'm going to set. So is there a way to set most k ones and satisfy all the clauses? Okay. So clearly it's in NP because a proof or certificate would be an assignment with at most k ones. I will just check that there are at most k ones, plug it into the formula and check that it is satisfied, right? And how do we show it's NP complete? And we want to reduce from some problem, some known NP complete problem, we want to reduce in polynomial time. So ideas? So you want to think about how does it, what problem does it look like, right? Okay, so one suggestion, reduce from vertex cover. Okay, so can you think of this as covering problem? You have a formula, right? The formula looks like this. Right. These are all have 2 clauses, 2 variables. Sorry, yeah, or. How do you think of a satisfying assignment as covering something? Yeah, so somehow satisfying assignment is covering the clauses, right?
Isn't it a disjoint edges like if for each clause for each edge I'll have a corresponding clause.
Okay.
So in order to
So okay, let's go slowly. Okay. So first thing is, even to think about what problem I want to choose from, first think of it as a covering problem where you want to cover the clauses using variables. Okay. So maybe vertex cover we pick. And what are we covering in vertex cover? We are covering edges with vertices. So it tells you what the clauses should be. Should be edges, right? Okay, so we will vertex cover polynomial time reduces to this. Let's call this min weight 2CNF. Right. So let's call this. Think of it. So I want minimum weight CNF. Okay. So what is the input instance here? G comma K, right? I'm looking for a vertex cover of size K. So you take an arbitrary graph and an integer K, which is an instance of vertex cover. We want to convert it into this instance. So you need to give me a 2CNF formula and a K. With what property? That G has a vertex cover of size K if and only if this has a satisfying assignment with K ones. So what is the formula? What are the clauses? So for each edge, UV, right, in this graph, we will have a clause. What is the clause? Yeah. So let's say I have a variable for every vertex. I'm going to say XU or XV. That's it. I have the entire formula out there. So in some sense, this is a generalization of vertex cover, right? This is vertex cover is where there are no negations at all. So since vertex cover is hard, this will be harder because it's more general version. Okay, so now it should be easy to see, right? If you have a k-sized vertex cover, you pick the corresponding variables corresponding to those k vertices, set them to 1. That will satisfy all the clauses. Conversely, if you have k variables that will satisfy all these clauses, note that this is always satisfiable because it's a monotone formula. There are no negations. It's always satisfiable. So if you have a k variable assignment that will satisfy this, pick the corresponding vertices. Okay. So the reduction is fairly simple. I mean, once I give you this problem, it looks like very mysterious. But once you connect with the problem, well, there are reductions which are very heavy, like one we saw from vertex cover to Hamiltonian cycle, but I mean, that requires a lot of work. But the kind of problems you are going to see in your assignment or exam are going to be of this type. Okay, let me assure you that. So just make the right connection, and then you will, and make sure that you follow through all the steps. You have to show it is an NP. You have to show a reduction. Make sure the direction of the reduction is correct. You have to show that the reduction is polynomial time, and then prove the equivalence condition. Then you are done. Okay, good. So we've seen variety of examples for NP completeness. Now let me spend a little bit of time talking about decision. We already discussed this. Decision versus optimization, right?
So two side is easy because it can be represented by a simple graph data in a simpler way. Whereas three side onwards is difficult. That's the reason, right? Or how do you say it?
I don't know what you mean by two sat is easy.
Two side is solvable, but
Yeah.
three side
What is your reasoning for that or
as in
intuition?
the edge like the clause in itself can be represented by edges or something.
No, not necessarily, right? These monotone two sat is fine, but if you have a two sat which has negations and so on, it's not clear how you will write it as a graph. If you have negations in the formula, you can write it as a graph. Oh, how?
As in you make pairs of x1 x1 bar, x2 x2 bar,
Okay.
and you keep on deleting edges, or let's
What
say you
will
have
be?
all the edges to start with. Not
What are the edges? Okay. Oh, I see.
like putting all the vertices.
Okay, you have a complete graph. Okay.
Yeah.
Hmm.
And then xi and xi bar won't have edges to start
Yeah.
with.
Okay. So it's like a bipartite graph in some sense. No. No. Okay. Fine. Fine. Yeah. Okay.
And then maybe x1 or x2. So then we delete the case where x1 can be 0 and x2 can be 0.
No.
And that one,
Yeah, I don't completely follow your line of
as in
thing.
I will delete the HBA between x1 bar and x2 bar.
And finally, you will make it a vertex cover problem. What are you going to make it finally in the remaining graph?
It will be like a tree problem, something like that.
Because if you reduce it to vertex cover, it doesn't help you.
No, I'm not ready.
Okay. So I don't know what the graph finally what it becomes, but here it is. I mean, here is the hint why 2 sat is satisfied. Suppose I have a class which is, so let's say I'll convert it into a graph problem. Okay. So now what we are trying to do is you're given a 2 sat instance and you're checking for satisfiability. Okay, no min weight. Is it satisfiable? So I will have a vertex for each variable and vertex for each negation. So there will be 2 n vertices. Now, if I have a class which looks like x or y, then can you say it in sort of implication? Something implies something. What implies what? Yeah. So x bar implies y, right? Because in a satisfying assignment, if x is set to 0, then y better has be true. Similarly, y bar implies x. So let me draw these edges, make it a directed graph. In my graph, I am going to draw these edges. Okay. Now, so you do this for every clause, you draw these 2 pairs of edges. Every clause corresponds to pairs of edges. Okay. Now, what does a directed path mean in this graph? Suppose you have a directed path from x to y. What does that mean? X implies y, right? So if you set x to true, you have to set y to true because that's in a transitive closure of this, right? So what does a path from x to x bar mean? What does it mean? That it's not satisfiable. No, let's read it carefully. What does a path from x to x bar mean? If you set x to true, this implication tells you x has to be false, which is meaningless. But that doesn't mean anything. That means that x has to be set to false. That is allowed. Okay. So somehow from this graph you get some assignments. What if you also have this? So x implies x bar implies x. Then it is not satisfiable. Okay. So somehow you convert it into this implication graph and look for some structure in the graph which will tell you whether it is satisfiable or not. That's a way to actually solve. So the way I have drawn my edges, the semantics of this is that if x is set to 0, y has to be true in any satisfying assignment. So generally if I have an edge from x to y, which means that x is set to 1 means y should be set to 1. Because here x bar is set to 1 implies y is set to 1. So x is set to 1 means y is set to 1, which, and suppose there is an edge from y to z. These z's and they could be bars as well, which means if y is set to 1, z should be set to 1. So if x is set to 1, z should be set to 1. So a long path from x to x bar means that if x is set to 1, it tells you x bar should be set to 1, which is meaningless, which means that x can be set to 0. But if you also have this, then somehow the clauses tell you that this is not satisfiable. So basically draw this graph, look for what kind of structures will forbid you to have a satisfying assignment, then find such structure. So you need some if and only if condition in that graph. Okay. So I won't say more than that. Okay, so let's get to decision versus optimization. Okay, so last time I said, okay, the whole NP completeness theory is all about decision problem, which is not too much of a problem, because if you want to solve the optimization problem, you can call the decision problem several times, right? So let's say we want to solve TSP, traveling salesman problem, where the question is given a weighted graph, weighted complete graph. I ask, is there a tour whose total weight is at most k, right? Suppose I have an algorithm to solve that. How can I use it to find the minimum weight TSP?
Take some arbitrary k,
Hmm.
and if it works for it, then you keep on going lower. Like you can half it or something, and you can do a binary.
So, yeah, do you
But
see
then
that? So,
there's a
so basically the idea is that you can do binary search. So, in what range?
or you just start with 1, 2, like 4, that kind of
Okay, how far?
till the maximum weight.
Well, yeah, so
Summation of
summation of the weights could be an upper bound, right? Or even if the maximum weight is some k or L, then look at n times L as the upper bound and 1 as a lower bound, and just do a binary search. Is there a TSP tour of weight at most this much? And if it says no, then you double, otherwise you half. So in log of n times k queries, which is polynomial in the input size, okay, that you can actually solve the optimization problem. Okay, so typically for many other problems, you repeatedly ask a decision question, you can solve this. Now I ask this question: decision versus search. This is interesting and little more tricky. What is the question? So I have an algorithm which will tell you whether there is a TSP whose total cost is at most k or not. Okay. Suppose the algorithm says yes, there is a tour whose total cost is at most k. How would I find that tour? At the moment, I only have this oracle, this algorithm, which will tell you whether there is such a tour or not. I want to repeatedly call this algorithm and actually find the tour. Is that possible? How do I do it?
keep on deleting edges.
Keep on deleting edges. Okay.
So if it says yes still, then we can delete that edge and be fine.
Okay. So one idea is that let's work this on the simpler problem of finding a Hamiltonian cycle. Right? Yeah. So you are given a graph. You want to know whether there is a Hamiltonian cycle, right? Unweighted, not complete graph. And I have this black box which you give this graph, it will yes there is a Hamiltonian cycle or not. And suppose it says yes, actually I want to find the Hamiltonian cycle. So what do? I delete one edge systematically and run this algorithm. It says yes there is a Hamiltonian cycle, still that means that that edge is useless, throw it out. And if it says no, there is no Hamiltonian cycle, that means this edge is critical, keep it. Right? So you do this for every edge, and then what?
So we just take those edges which were very crucial, and it should form a Hamiltonian cycle.
Okay, so the answer is that take those edges which are critical, right? For which the algorithm said no without it, and collection of edges, do they necessarily form a Hamiltonian cycle? At the end, they should. Okay.
Because
And after removal also, it may be the Hamiltonian cycle of the new graph. But when I add,
Number of vertices doesn't change.
no, when I'm doing
So,
an edge,
so if when I remove an edge and it says yes, there is Hamiltonian cycle, that means this edge is not needed for the Hamiltonian cycle. If it says yes, there is no Hamiltonian cycle, I put it back and move on to the next edge. I keep doing it. So I do some n choose or number of edges times query this. And the claim is at the end, what remains, the critical edges, is a Hamiltonian cycle. Why? Because if you have Hamiltonian cycle and some more things, right? But when I probed this edge, it should have said, I don't need you, right? So what will remain is the Hamiltonian cycle, and you can get that, okay? So that's an useful thing you can, I don't know whether there's a general theorem, but this is a trick you can apply for many of the NP-complete problems.
Does it work for all?
Even then, no problem. Even if there is a unique Hamiltonian cycle, it will do the same job. Does it work for, proving such a general theorem requires proper formulation of the problem and things like that, but it usually works for all the problems. So that's something useful to know. Okay, good. So now let's move on. So we know how to prove problems NP-complete, but we need to deal with, there are now hundreds, thousands of problems which are NP-complete. Somehow we need to deal with them because they occur in practice. Okay. Now, what does a problem is NP-complete mean? What does it tell you about the problem?
At least as hard as the other.
Yes. So, in terms of coming up with an algorithm, what does it tell you? Yeah. So, pi is NP-complete means unless pi p is equal to NP, these two clauses collapse. There is no polytime algorithm. So let's look at the corresponding optimization problem, which is what I care about. That will solve the problem exactly. For all instances of pi. Okay, that's the most general instance of pi. You cannot, there is no polynomial time algorithm which will take any instance of pi and it will run in polynomial time and give the exact answer. Okay. So now we can relax each of these conditions. What is this? Okay, so you can ask, oh, P equal to NP, what are other kind of complexity assumptions we can make? Polytime algorithm, okay, you want me to settle for something non-polynomial time, but what is the best non-polynomial time algorithm you can come up with? You can say, oh, I don't want to solve necessarily exactly. I'm willing to settle for some error, some approximation. And the other thing is that maybe I don't want to solve it for all instances, but some special instances, right? So each one is a direction by itself, is a course by itself, right? So this leads to this area of structural complexity theory. Where we don't look at problems, but groups of problems, find relationships among them, find hierarchy of complexity classes, and talk about which ones collapse, which ones don't. What are some other weaker conjectures by which you can show this. That's the area there. Here, exact exponential algorithms, right? Yeah. So, for example, we already saw some examples. You want to settle for best exponential algorithms, but even in the exponential world, there are different kind of functions. So give me something efficient, right? So we saw an improvement from 2 power m to 2 power n for set cover. Both are exponential algorithms, but this is better than that, right? K power n to some 2 point for coloring, right? We saw this using dynamic programming. And we'll see maybe one more example of this. So this is a whole area. There are problems for which you can even get 2 power square root of n algorithms. So something better than brute force. Now, not even clear that everything can be solved in 2 power n, right? So for example, TSP, what would be a brute force algorithm? The traveling salesman tour, which is the minimum cost, what would be a brute force algorithm? N factorial, right? Because you want to run through. In fact, later we will see, maybe today or next time, n factorial can be improved to some 2 power n square for TSP, right? This we have seen. Sometime we will see this, okay? So this is the area there where we want to live with the fact that we have to obtain exponential algorithm, but I want some good exponential algorithm. Yeah, so for example, 3-SAT can be solved using some 1.5 power n instead of brute force 2 power n. Vertex cover has some 1.2 power n. Okay, these are all some of the developments in this area of exact exponential algorithms. This opened up this whole industry of approximation algorithms. We'll see some today and on Friday maybe, where, so this is applicable for optimization problems, which is what we care about, where you say, okay, the exact optimum is hard to obtain in polynomial time, but in polynomial time, what is the best close to the optimum you get? Now, the challenge here is, how do I even measure how close my solution is to the optimum, right? People apply some heuristics, some simulations get some answers, but you never know how close it is to the optimum. But here, in theory, we will actually look at the ratio between the optimum and my solution and give a bound for it, even without knowing the optimum solution. We will use some bounds for the optimum to prove this. Okay, again, that's a whole course and big industry by itself. And this is where you say, okay, I don't necessarily want to work with a general graph, but let's say maybe my graph is special. Can I solve this problem better, right? So for example, we saw click is NP-complete in general graphs. Independent set is NP-complete in general graphs. What about click in bipartite graphs? We don't have it. So yeah. So in a bipartite graph, what can be the max click size? 2, right? Because you can't even have a triangle. If you don't have a triangle, you can't even have a larger clicks. So it's completely trivial problem. Okay. So that's now this is one extreme, but a non-trivial example is vertex cover in bipartite graphs. So vertex cover. Oh, by the way, we already saw one, right? Maximum independence set. So let me write this, click in bipartite graphs. Trivial, not just polynomial time, but maybe, yeah. Max independent set in interval graphs. Okay, so here, the special instances, particularly in graphs, there is a whole industry of special classes of graphs: bipartite graph, chordal graphs, interval graphs, permutation graphs, all kinds of things. So, what is an interval graph? I already told you about it. So, it is characterized by a set of intervals in the real line. Okay, so the vertex set for your graph corresponds to the set of intervals. So, each interval gets a point and you draw an edge when these two intervals overlap. Okay. And what is a maximum independent set problem in that interval graph? Maximum set of non-overlapping intervals, and we saw using dynamic programming greedy that you can actually find it, right? Just order them by earliest finish time and just in a greedy fashion take them out. So, you can actually solve, even though it is NP-complete in general graphs, you can solve in polynomial time, in linear time, in interval graphs, and for even larger classes of graphs. So, here the interesting thing is what is the boundary, right? Like 3 sat is NP-complete and 2 sat is polytime. You need to know, so here is this big class of graphs where it is polytime, and then if you go above, it becomes NP-complete. That kind of a boundary would be nice. Okay. Min vertex cover in bipartite graphs. Right? You've seen this in discrete math course. There's a famous theorem called conics theorem, which tells you that maximum matching is equal to the size of the minimum vertex cover in bipartite graphs. Right? Have you seen this in the discrete math course in graph theory? So basically, you can find the maximum matching, which we know we can do it in polynomial time. You can apply flow, and once you find maximum matching, you will be able to find a minimum vertex cover in bipartite graph. Okay, so so this is polytime solvable because maximum matching is polytime solvable. Okay, I mean I don't know whether do you remember how the so one direction is easy, right? What do we know? Always in any graph, it's useful to know there is a relation between maximum matching and minimum vertex cover, which is larger. Vertex cover is larger, right? Because from each of the matching edges, you need at least one to cover that edge, and that won't cover any other matching edge. So, you need one from each of the matching edges. So, minimum vertex cover size is at least maximum matching, but in bipartite graphs, they are the same. Can you think of an example where they are not the same in general graph? Even simpler. A triangle, right? If you, in a triangle, maximum matching is 1, whereas minimum vertex cover is 2, because one vertex, if you pick, it doesn't cover this edge, so you need at least one more. Okay. So, this proof essentially says, okay, you find the maximum matching in this bipartite graph, and somehow you can pick exactly one vertex from each of the matching edges to cover all vertices. Okay. So, roughly the proof goes by look at unsaturated vertices here. Okay. Maximum matching may not saturate all vertices. Look at unsaturated vertices, and they may have edges there. I mean, if they have edges at all, the other endpoint should be a saturated vertex, right? Why?
Because if not, then we can
If not, you can make that and increase the matching. So, the other endpoints are all going like this. So, to cover these edges, we are going to pick this, because remember, my goal is to pick exactly one vertex from each matching edge and be done with it to cover all edges. So, natural choice is anything unsaturated, any edges incident on them go here, I pick the other neighbors. Then I am not going to pick these guys, because you told me you are going to pick only one from each of the matching edges. So, if they have some neighbors, pick them into your solution. Keep following this, right? Basically, any unsaturated vertex, any vertex which is at a distance, odd distance from here, you pick them in the alternating path. Similarly, you do the same thing for these guys. Okay, and for the remaining, you pick something arbitrary. Now, is it possible that for a vertex here, this guy is at some odd distance, and this guy is also at some odd distance, so you end up picking both? This is a matching edge. It's not possible, because if you do that, then you will get an augmenting path which increases the matching size. Okay. Okay. So it's about one paragraph or two paragraphs proof, but essentially, if you find the maximum matching, you can do a little bit more to work and compute the minimum vertex cover. So it's polynomial time solvable. Okay. So this is this area of special graphs. Let me write this. Right. So I'm not going to talk about this. I'm not going to talk anything more. So I will spend some time on approximation algorithms. There is one more. How can I miss? Okay, so this is somewhat related to exact exponential algorithms, where you want exact algorithm, nothing approximate, but I would say it's a combination of special instances, exact exponential algorithms, because somehow what is special, if you can parameterize it, then I want my algorithm to be exponential in that parameter and polynomial in the rest. Okay. So, we will see some examples of this as well. Okay. So, what I am going to spend will be some examples of approximation algorithms and parameterized complexity, and maybe also talk about this today and on Friday. Okay, good. Okay, so let's start with vertex cover. Remember, the goal is to pick a subset of vertices that cover all edges. And it's an NP-complete problem on general graph. What would be a natural algorithm, some sort of a greedy algorithm for this problem? So I don't know, I don't care about optimum solution, but some good approximate solution. What would be a natural greedy choice?
Take an edge and take its fruit and
That's not a natural. That's something because you knew it. Yeah, from I want to hear from there, the other direction, other side. What is the natural greedy algorithm for finding a minimum vertex cover? You want to pick vertices to cover edges. Did I wake you up? Yeah. Yes, go ahead. I can't hear you. Is the problem clear? No, okay. So you have a problem with mic. Okay. So I think not very hard to figure out. Pick vertex with the highest degree. Because that covers a lot of edges, right? So S is my vertex cover. And repeat. Okay. Repeat until G has an edge at all. Repeat until G has an edge. Right? If you've covered all the edges, it's fine. No, no. No, disconnected. What? Yeah. Come up with an example where this is not optimal. Not easy at all. Yeah, go ahead.
Take a star
Hmm.
and
Ah.
two levels.
Yeah, so you knew it. Okay.
Spider, I don't know what it is.
I don't know what the names are, but okay.
Is it like
Huh?
difficult to figure out?
Yeah, it's not. I mean, it's not that hard. Yeah. So, but even that, after I pick, I can do a minimality check. Then the middle vertex will go away. Okay. So here's give an example where this is not optimal. Right. So, the example he was mentioning was this. Okay. So, what would the algorithm do first? It will pick this vertex and delete it. Then you are left with a matching, you need to pick one from each. Okay. But if you just picked one from each, that itself is good enough. So, I could just do a minimality check and can I delete a vertex and see whether it still covers it and pick that and pick it. So, I mean, you can play around with patch more such examples together and do this. Okay. Now, the more challenging thing is I was talking, okay, so what are we interested in, right? It gives you some solution. How far is it from the optimum? What does that mean? How do we even measure this, right? So you can hear me, right? Yeah, so what I'm interested in, suppose AG is a solution produced by greedy on G, and I have opt G, minimum vertex cover size. The question is, what can you say about so clearly this will be larger than this. Why?
Otherwise, this would be the same. Otherwise, this.
No, larger, can it be smaller? This is my question. Will AG be smaller or larger?
It has to be larger.
Why?
Because if it would be smaller, then it would be, then the opt would not be.
I mean, it's a minimization problem. So this is minimum. So any other solution would be greater than or equal to that. So this quantity is greater than or equal to 1. Okay. So I'm interested in trying to find out how close to 1 it is. Of course, this is, yeah. So in particular, max over all G. Right. It turns out, again using some complicated argument, this is more like natural log. So it's and there are, so it's the ratio. Let's call this as approximation ratio, right? So I'm interested in what is the it's not, and there are examples where it can be as bad. என்னமோ ஸ்க்ரீனில் வருது இல்லை நம்ம ஸ்க்ரீனில் எது வருது
These students are
Checking
saying
some.
that there's something. I'm just messaging the.
Okay. Now the problem started, they were trying to ask me, அவங்களுக்கு ஏதோ வால்யூம் ப்ராப்ளம் ஆச்சு முடியல. So அப்புறம் they went around, played around with it. Yeah, so what best you can prove is that this greedy algorithm is never more than log n times the optimum, the solution produced, and there are examples where the ratio could be as bad as this. Okay. Okay. So we may do this later sometime, but you are welcome to. This is not. I mean, this requires some work. We will actually prove this in the context of set cover maybe, because that's a more general problem. This, think about it. And, all I can do is to throw you the graph, what that graph is. But yeah, it's not going to give you much insight into it. But it turns out a little non-intuitive. I mean, this is a more natural thing because it's the greedy and so this is algorithm 1. So another algorithm is this: find a maximal matching. Okay, it's maximal. Not that it matters. You can find a maximum matching also. Maximum matching, we know how to find it in bipartite graphs using flow, but in general graphs also there is a polynomial time algorithm. But maximal matching is even easier, much easier. Okay, so what is the difference between maximal and maximum? Maximal means that, you know the difference.
Maximum means it is related to all the other elements.
Maximum means it's optimum. Maximal means
I mean, any chain it's that.
maximal means
Does not exist on any other
I mean,
matching
there are
which,
elements that are not compared.
which is superset of that.
yeah, this can't be extended. There is no matching which is a superset of it, right? Which may not be maximum. So what would be an?
Maximum is the maximum over all maximals.
When you say superset, then it should be inclusive.
Yeah.
Yes.
So what would be? Give me an example where a maximal is not maximum. Okay.
Generally, stick a path of word length
Okay.
and
Yeah. Okay. So here it is, right? If I take this matching alone, it is a maximal matching because you can't add another edge to it. But this is not maximum because the maximum is this. Okay. So maximal matching is easy to find. How do you find maximal matching?
Pick an edge and delete all its edges.
Just greedy, right? Pick an edge, then delete all the edges incident on the other endpoints. Go pick an edge, keep going. So it's just linear time you can find. Then S is V of M, that is both endpoints of edges in M. Okay. For now, that's it. This I claim is a vertex cover and it's a good vertex cover. Claim 1. So all I'm doing is go to my graph, find a maximal matching. There may be a lot of edges like this. But all I do is pick both endpoints of every edge. Claim 1 is S is a vertex cover. And claim 2, cardinality of S is at most 2 times opt VC of G. Okay. Let's try and prove each one of them. Why is S a vertex cover? Take a maximal matching, pick both endpoints of each edge. I claim that together they will cover all edges.
Also, if it was not, we take for contradiction.
What is the
there exists an edge. Both vertices have not been taken, so we can add it to the matching.
exactly? So otherwise, it will contradict the fact that what you have is a maximal matching, because if you have an edge which is not covered by any of this, what stopped you from adding this edge to your matching, right? So that's obvious. Is this obvious? That because we saw that minimum vertex cover size is at least the size of the matching. Okay, so cardinality of minimum vertex cover is greater than or equal to cardinality of M, because M is any matching. So you need at least one endpoint, and all I have picked is 2 times M. Okay, so that means that cardinality of S is less than or equal to 2 times cardinality of M, which is 2 times. So which means the size of the whatever the algorithm produced by whatever the optimum is at most 2. It's a ratio 2 approximation algorithm. Okay. So even though we don't know the optimum, we are using a lower bound for the optimum. What is the lower bound for optimum we are using here? The matching size. Maximum matching size is a lower bound for the optimum, and that's what we are using here. Okay. And what is interesting that is that this is the best approximation algorithm we know for 30-40 years, and it is expected that you can't improve this ratio 2. Okay. There are actually a number of ratio 2 approximation algorithms for minimum vertex cover. I will give you another one. Yeah.
How is the maximal matching? We can find the better
Worse in what sense?
compared to the maximum matching. Minimum over maximum. The ratio will be better.
But that's I think an NP had problem finding a minimum maximal matching. Yeah. Yeah. Right. You can find a very small maximal matching, then twice of that is going to be small, that you would be close to optimum. Yeah. So here is another ratio 2 approximation. So what I want you to pay attention is that we don't know the optimum value, but we are using some upper bound, and in this case we are using this as the a lower bound or upper bound, depending on it's a minimization problem or maximization problem. Okay, so what I want to do is to formulate vertex cover as some sort of a linear program. Okay, we really didn't do linear program in this course, but hopefully some of you know this. So I want to come up with some variables. So I are given graph G, and we want to write some optimization linear programming. What is linear program formulation of a problem? You want to minimize some linear objective function, okay, linear constraints on the variables. So you have some variables, you want to optimize, minimize, maximize some linear constraints on the variables subject to some linear constraints on the variables, okay, a bunch of linear constraints. So what is the natural way to formulate it as a linear program? What are the variables and what do you want to minimize? N variables. Okay, so let's say variable corresponding to vertex V. So what do we want to minimize? Number of vertices in the solution. So it is, so what is the interpretation you want to give for this solution? It can be 0 or 1. So 0 means, or 1 means in the solution 0 means not in solution. If that is the interpretation, what is it you want to minimize? Summation xv subject to what are the constraints? For any edge uv xu plus xv is greater than or equal to 1. Okay, that essentially one of them has to be 1. At least one of them has to be 1. Plus, you also have this constraint that okay. Now, this is actually called integer linear program because you are forcing the variables to integers. If you don't have this constraint, this is linear program and you can solve it in polynomial time. But with this constraint, integer linear program, what do we know? Is it NP complete? Yes? Okay. Well, I mean, you can formulate it as a decision problem. Is the optimum at most k? We just proved it's NP complete. Do you see this? What did we do? We reduced vertex cover to this, right? Right? We proved 0, 1, in fact, restricted 0, 1 integer program is NP complete. What did we reduced vertex cover to this, right? G has a vertex cover of size at most k if and only if there is that the solution to this, the optimum is at most k. If I put this constraint, right? So, this clearly because we have reduced a known NP complete problem vertex cover in polynomial time to this. Okay, it turns out if the graph is bipartite, you don't even need this constraint. That somehow the fractional solution will also be integral, and that's what makes the problem polynomial time. Another explanation for why bipartite graph is vertex cover. So, the graph has a nice structure that the linear program itself gives you integral solution if the graph is bipartite. Okay, that apart. Okay, now it's NP complete. What can I do now, right? What is my goal? I want to design an approximation algorithm. So, let me remove this constraint. Then I know I can solve it in polynomial time and solve them. Okay, and then see what we can do. Solve what is called LP relaxation of vertex cover LP, right? So, that means you remove this constraint and simply say xu is greater than or equal to 0. Then I am telling you that that is an LP which can be solved in polynomial time. There is a black box, apply that and get the solution. Now, we want to convert it back to a vertex cover from the LP solution, right? Because LP solution, because we created this set of inequalities and optimization and gave it to LP. LP comes back in solution, and if LP gives me 0 and 1, that's great. But LP may not, right? Because it's going to give you let x star V in V be the LP opt. First of all, they will all be between 0 and 1. Why? I mean, I didn't even put that constraint less than or equal to 1. I could put it in, but I don't need it. Why? You see that? Hmm?
It can't be greater than 1.
Why?
We have put the constraint that it's greater than 0.
Greater than or equal to 0, but it can be greater than 1.
If it is greater than 1, you can just reduce it to 1.
If it is greater than 1, bring that variable all the way to 1. It doesn't violate any of the constraints. It brings the optimum down. So there is no reason for optimum solution to have some xv values greater than 1. So they will be between. So xv star is between 0 and 1. So it will be fractional value. Okay, now I want to pull out a vertex cover from the LP solution. What is the natural thing to do? Yeah, so let's do some roundup, right? So now let S, I'm going to tell you, is set of all V in V such that xv star is greater than or equal to half. Okay, I'm going to say pick all the vertices which the LP, which I can solve it in polynomial time, gives me solution greater than or equal to half. Now I claim these two things. Claim 1, S is a vertex cover, and claim 2, cardinality of S by opt is at most 2. Okay, so which is easy to prove? First one is easy to prove. Why?
If there is any edge which has not been covered, then it means that both the endpoints had xv less than or equal to 1, which is not possible.
Less than half. So basically, my xv star satisfies these constraints. So since it satisfies this constraint, for every edge, at least one of them must be greater than or equal to half, because if both are less than half, this constraint will not be satisfied. It's a feasible solution which minimizes it. Okay, this is true as for all uv in E, xu star plus xv star is greater than or equal to 1. Claim 2. What is?
The value of this, the linear programming relaxed.
The value of, okay, so let me just say summation xv star v in V
Is at least half into S.
is at least half into S. Okay, so in other words, you are saying cardinality of S, this is easy to see, is 2 times this, because what did I do?
Because half is contributed.
I've just, yeah, if it was half, I pushed it to 1, so I would have doubled each value, right? So let's write it this way, that cardinality of S is equal to summation 1 for every vertex in S. Okay, for every vertex in S, I say 1. Now, this 1 I claim is 2 times xv star. Okay, so I can even say, yeah, so I think I can even say is less than or equal to 1 for every v in V. Okay, now this 1 is less than or equal to 2 times summation xv star v in V, because whenever I got 1, xv star was greater than or equal to half. Okay, I don't need to do this roundabout, not this. This is less than or equal to 2 times which is less than or equal to summation 2 x v star v in v. Yeah, that's a better thing to write. So, for every vertex in S, I am putting 1. Why did I put it 1? Because x v star was at least half. That is why I set it to 1. So, that corresponding x v star into 2 must be greater than or equal to 1. Because this is the same as saying x v star is greater than or equal to half. So, 2 x v star is greater than or equal to 1. Now, I expanded it to include all vertices. Now, this is equal to 2 times LP opt. Remember, because x v star is the one which minimizes this overall thing. What can you say about LP opt and minimum vertex cover? LP opt is smaller. Why? Because, yeah, so it will 2 into, right? Because it's a minimization problem. I relaxed some constraint. Whatever the minimum vertex cover, you put the variables set accordingly. That is also a solution to the relaxed thing. So, that will also come in. By relaxing, I might even go lower because it's a minimization problem. So, what I have is that the size of S I produced is at most 2 times minimum vertex cover. Okay. Now, the interesting thing about the LP solution is that suppose I want to talk about weighted vertex cover. Okay. Suppose every vertex has certain non-negative weight or some cost, and among all vertex covers I want to pick the one with the total minimum weight. Okay, that's just the weights are all 1, it's the same as cardinality vertex cover. So, I could talk about weighted vertex cover where I have every vertex has a non-negative weight and I want some integer weight. I want to pick the subset of vertices. So, it may not be the smallest cardinality because some vertex may have a larger weight and you might. Now, this algorithm is not so easy to adapt for the weighted case because this simply says find the maximal matching and we argued it's at most 2 times. It certainly gives you a vertex cover, but I can't argue this because here when we say opt, we are talking about with the weight. But this algorithm is trivial to modify for the weighted case. Tell me what I should do. Just look at it and you will see.
Add some extra constraints that
Constraint is every edge should be covered. There's nothing else. What are we minimizing?
weights into
I'm trying to minimize the constraint is it's a vertex cover. Every edge should have this. Run the whole thing. Take the XV star, do this. Now I claim the weight of S is at most this because this whole thing summation WV V in S, which is less than or equal to 2 times WV into XV star, which is less than or equal to okay, so optimum minimum weight. Okay, so the LP is very useful for solving the weighted vertex cover in one shot. Okay, let's do approximation for another problem. Okay, is that clear? Any questions? Yes. LP will solve it. Yep. That's a good question. LP will solve it because of the matrix. The constraint matrix is what matters for integral versus fractional solution. Okay. The next problem we want to talk about is traveling salesperson problem. Okay. So recall you have a complete graph, weights on the edges, and you want a tour which minimizes the total cost. With NP-complete we have seen, I want to come up with some approximation algorithm, right? So here is interesting first result. Unless P equal to NP, there is no constant factor approximation. In fact, okay, this is sort of a negative result. The constant actually can be even pushed to even polynomial factor approximation and things like that. So that means that, yeah. So how do I prove something like this? It's actually fairly easy. I mean, even though it looks pretty strong because you're talking about. Okay. Yeah, okay, contradiction. So suppose there is a constant factor approximation algorithm for TSP. Then you want to show, what do you want to show? P equal to NP. How do you show that? Give a polynomial time algorithm for an NP-complete problem. What's a natural NP-complete problem you can think of here for which you want to give a polynomial algorithm? Hamiltonian cycle. Okay. Okay.
This might be because the weights.
Your choice, right? So what do you want to give the weights to? So let's prove this and then we'll see how much we can push this, right? Suppose there is a C ratio approx algorithm for TSP. We will give a polytime algorithm. So in fact, we use a TSP algorithm to solve Hamiltonian cycle to show that TSP is NP complete. But there it was exact algorithm. Now you are saying no, even if you have some little bit of approximation, I have enough leeway to solve Hamiltonian cycle. That's what we are saying. Okay. So you take your Hamiltonian cycle instance, you are given G, right? Some graph. I want to create an instance of TSP. So that means I have to make it a complete graph, put some weights on the edges such that something happens, right? Even an approximation algorithm for TSP gives me a Hamiltonian cycle. So what should I put the edge weights? So weight of UV, I'm going to put as the following. Yeah, weight of UV is 1 if UV is an edge in the graph and it is n times C, right? Or maybe n times C plus 1 otherwise. Okay. Approximation C factor, and n is given number of vertices. I am going to put this weight. Okay. So, now what can you claim about this weighted graph? So, let us call this some G prime, which is basically G with weights added, right. G has a Hamiltonian cycle, implies G prime has a Hamiltonian cycle with total cost at most n, in fact exactly n. G does not have a Hamiltonian cycle, implies any Ham cycle in G prime has cost strictly greater than Cn, because it will use one of these edges. Okay. So, that is it. So, now I give it to my approximation algorithm. Tell me, give me an approximate to the optimum. Okay. So, if it has a Hamiltonian cycle, there is one of cost at most n. So, the approximation algorithm will give me a solution whose cost is at most Cn. Okay. There is no really Cn thing is only n. And converse, and if it gives me a solution whose solution is more than Cn, then I know that, in fact, in fact, this is if and only, right, that if any Hamiltonian cycle has cost more than Cn, G does not have a Hamiltonian cycle. Right? Because if the approximation algorithm produces something strictly greater than Cn, that means the optimum is greater than n, right. So, that means there is no Hamiltonian cycle. If the approximation produces something at most Cn, then we know that G has play around the weights in a way that even an approximation algorithm for TSP is useful for. Is that clear? Okay, so this is hopeless. In fact, C can be even any polynomial in n, because as long as the weights are polynomial, we are talking about. So, no polynomial ratio approximation algorithm for general TSP. Okay. But what we will see for a special TSP, we will call what is called a metric TSP, where what is metric TSP? Where the distances satisfy triangle inequality. What does that mean? The distance between, for any triple UVW, remember what we have is a complete graph. There is a distance between any pair of vertices. DUV is less than or equal to DUW plus DWV. Okay. So, always directly going to a vertex is cheaper than going through some other vertex. Now, we will design approximation algorithms for this special instances of TSP where the distances satisfy triangle inequality. Okay. Is it still NP complete? Good, natural question. Is it still NP hard? Because maybe it's even polynomial time solvable. Why do we want to? Is it still NP hard? Yes, you gave a proof last time. Yeah. Right. Note that metric TSP is NP hard because last time we saw TSP with weights 1 and 2 is NP hard. Remember? When we reduced from Hamiltonian cycle, we said the edges get 1, non-edges get 2, then Hamiltonian cycle exists if the total cost is at most 1. 1 and 2, I claim, satisfy triangle inequality. The weights are all 1 and 2. Let's look at 3 points U, V and W. I claim that DUV is less than or equal to DUW plus DWV, right? Because each one of this is at least 1 because the weights are 1 and 2. So the sum is at least 2. This is at most 2. Okay. So metric TSP is NP hard. So what we will do next time is for this special instance of TSP, design some good approximation algorithms using simply minimum spanning tree, which we have seen in this course. Okay, so I'll do that and then give the TSP better exact exponential algorithm and maybe another approximation on Friday.